Hello, welcome back to Algebra. The title of this lesson is called Solving Equations that are in Quadratic Form. This is part one of several lessons. Now, if you've been working with me up to this point in algebra, we've been working with quadratic equations, otherwise known as parabolas, for quite some time. And you might be saying, well, don't we already know everything there is to know about these quadratic equations? Why do we continue to work on this? Well, the answer is, quadratic equations are just that important. They are so very important. There's a lot to it. So what we're going to be doing in this batch of lessons is kind of finishing up the discussion with quadratics. This lesson will be talking about equations, what we call, that are in quadratic form. And I'll show you what that means in a second. But I want to give you a little bit of a roadmap for this batch of lessons in the sequence. Pretty soon, in the next few lessons after this topic, we'll be talking about how to take these quadratic functions, these parabolas, and how to shift them around the xy plane. In other words, you already know about f of x is equal to x squared, right? It's that nice parabola centered at the origin. Well, we can change that equation slightly and we can move it to the left, we can move it to the right, we can move it up, we can move it down. So we're going to be learning how to shift these equations around, and we'll have some computer demos as we get to that point to show you graphically what's really going on. And then we'll actually be wrapping up the class with this batch of lessons with learning how to take roots of a quadratic equation. We already have the roots, and how to go backwards and reconstruct a quadratic function that is apparent, or that the roots come from. In other words, if I give you the answers, the roots, how do you go backwards and construct the quadratic equation from that? And in between here and there's a lot of little details and theorems that we have to cover. And so I want to just kind of give you that overall idea that these quadratic functions, these quadratic equations, are so very important. One parting thought as I want you to keep in the back of your mind as we do these batch of lessons, is just one little example that occurred to me I want to bring up to you. A lot of students say, why did we spend so much time on quadratics? Well, as I said already before, they're ubiquitous. They're everywhere in science and math. And I'll give you one example of that. I'm not going to write anything on the board. I just want you to kind of work with me. This is kind of advanced, but I want you to understand how useful they are. When you get past algebra and you go on into calculus, and you get past calculus, you're going to take a class called differential equations, which is an advanced calculus class. That's all it means. But differential equations is really how the world works. It's all about using calculus to predict how complex systems are going to move. And probably one of the most famous differential equations in advanced calculus you probably even have already heard of, and it's the famous Newton's second law of motion, F equals ma. If you haven't taken a physics class, maybe you haven't heard of that, but certainly it's one of the first things you learn in a basic physics class. Force is equal to mass times acceleration. It turns out when you get past basic physics and you kind of decompose that famous equation, it turns out to be a differential equation, which means a calculus equation. And the reason I'm bringing all this up, because it seems like it's coming from nowhere, is because that famous equation, F equals ma, when you break it out into the calculus notation, is actually what we call a second order differential equation, which means it has a second derivative, or a term that has the calculus derivative taken 2 times in it. Why do I explain all of this to you now in an algebra class? Well, the reason is because when you learn how to solve those equations, those second order differential equations, the solution method that we all learn when we take those classes down the road, as part of that solution method, you have to solve a quadratic equation because it's a second order differential equation. It ends up requiring us to solve a second degree polynomial, which is a quadratic equation. In other words, one of the most famous equations of all time that's used to calculate trajectories to the moon, that's used to calculate anything, moving around on the surface of the earth in terms of physics, which means force is equal to mass times acceleration. When you grow up a little bit, so to speak, and really deal with that thing in terms of calculus, you end up having to solve these quadratic equations in the process of solving that advanced calculus equation. So we're building the bedrock here of things that will be used for many, many years if you're going to go into any branch of science and engineering. So now that I had to get that off my chest because I want people to understand why we're learning things, let's turn our attention to what we call solving equations in quadratic form. So I'm going to go and start with the beginning here and show you a quadratic equation that I know should look pretty familiar to you. What if you had the equation x squared plus 4 times x minus 3 is equal to 0? You all know how to solve this many, many different ways. We can try to factor it and solve it. We can try to use the quadratic formula, and of course we'll be able to solve it. We also know that we can complete the square on this thing and solve it. So we have now basically 3 main methods of trying to solve this thing. but it's a quadratic equation. But more specifically, I want to write something down here. This equation is what we call quadratic in the variable x. I'm putting x in quotations. You'll see why in a second. Why is it quadratic in x? Because x is the thing that's squared, and then plus a number, 4 in this case, times x, and then plus or minus a number, and then really there's an invisible x to the 0 power. Because remember, anything to the 0 is just 1. So really you have an x squared, an x to the first, and an x to the 0, which is invisible because anything to the 0 is 1, so it just disappears. That's the general form of these things we call quadratic equations. The thing that is being squared is just the variable x, so we say it's quadratic in the variable x. Now let's use the same thing as a skeleton and introduce a similar equation. What if I give you 3x plus the number 1, right? I'm going to square that. And then I'm going to add to that the term 4 times 3x plus 1. And then I'm going to subtract 3, and I'm going to have this equal to 0. Notice how this is exactly the same thing, except for one huge difference. The x squared is replaced by 3x plus 1. This whole quantity is what is now squared. The number in front of the x is 1. This is a 1 here, and there's a 1 in front here. There's a 4 in front of here, and then a 3, and the negative 3 is the same as well. So you see how it matches the pattern exactly. Something squared plus 4 times something minus something as a constant, and all the numbers are the same. The only thing is we've swapped this guy out. So what does that mean? It turns out this is a quadratic equation also. It looks more complicated than this one because of the more complicated thing that's being squared and that's carried through into the other terms. But this one's not quadratic in x. We say this one is quadratic. Can you guess what? In the quantity 3x plus 1. So this one's quadratic in x because that's the thing that's being squared. The second one is quadratic in a totally different term, right? So let me give you one more example and we're going to start to solve a problem. But this is the goal of this lesson is to teach you how to solve equations like this. They're quadratic, but they're equations in quadratic form because this is the quadratic form, but it's more complicated than what we've dealt with in the past. So here's another example. What if I give you 1 over 3x, quantity squared, whoops, not to the third power, we don't know how to solve those yet, to the second power, plus 4 times the quantity 1 over 3x, minus 3, and this is equal to 0, right? So same sort of thing. It matches the form exactly, something squared plus 4 times something minus 3, but this one is quadratic in the quantity 1 over 3x. So these are all quadratic equations, right? It's just that this one is quadratic in the simple variable x, and the other ones are quadratic in the more complicated terms. So what we're going to do now is learn how to solve these. Now, the first thing you can do, of course, when you're given any equation like this, is you can just brute force through it. In fact, if you wanted to solve this one, you already know how to do it. Because if I cover up the rest of the problem, you know how to expand this thing, right? This is a binomial times itself. So you can multiply that out with FOIL, right? With this one, you can just take the 4 and distribute in. That's going to give you a bunch of terms. And then the minus 3. So when you expand this whole thing out, you're going to get lots and lots and lots of terms. And then you collect like terms. And so you'll have a new quadratic equation, which you can then try to solve. Of course, you can always do that. That's what we call the brute force way of doing it. You just expand that sucker out and try to collect terms, and then you're going to get a quadratic, and you solve it using quadratic formula or other methods that we have learned. But what we're going to do in this class, or in this lesson, is we're going to learn how to solve these things in a much more clever way. We're going to use the concept of what we call substitution. And you're going to find that it's actually really cool. It makes it much, much easier to solve than blowing this whole thing out, which is, most people would probably try that first, including me, if I wasn't thinking clearly about it. But when we use the concept of substitution, it's going to make it much, much simpler to solve this. Also, in the back of your mind, I want you to keep in mind the idea of substitution, because when we get to calculus later down the road, probably half of the class, and I do mean it literally, about half of the calculus class is using a concept called substitution to solve problems in calculus. So this idea of substitution actually goes way beyond algebra. And so we're kind of inching our way into what this means. But you'll be using substitution for many, many years to come. So let's just talk about this first problem right here. Now, I don't want to solve this particular one. I want to solve one that's a little bit easier first. So let me give you another problem. This will be, I'll call this problem 1a. What if I give you x plus 3, quantity squared, minus 5 times x plus 3, plus 4 equals 0. Now this is a quadratic in the quantity x plus 3, because that is what is squared, that's what's to the first power, and that's what's to the 0th power there. So it's a quadratic equation. So what we're going to do is we're going to make a substitution. And you're free to make any substitution with equations that you want. The goal with the substitution is to make the equation simpler to solve. If your substitution makes it harder to solve, it's the wrong move. But if your substitution makes it easier to solve, it's the right move. And you'll see how that happens right here. This guy is the obvious thing that we want to substitute. So we're going to say we're going to let some new variable, which isn't even in this problem, we're going to call it z. You can call it what you want. But I'm going to say let's let z is equal to x plus 3. Why did I choose x plus 3? Because we know that this thing squared minus 5 times this thing and so on is in the quadratic form. So we're going to basically take this thing and represent it as a new variable, because then when we do that, we can make this substitution. Since z is now equal to this, we can say that I have a new equation called z squared minus 5 times z plus 4. Make sure you understand before we go on that these two equations are the same. Exactly the same. Because now that we've let z equal to this, if I take this and stick it in here, I'm going to get the first term back. If I take it and stick it in here, parentheses, don't forget, it's equal to this whole thing, so you'd have to put a parentheses. That would give me this term, and then the 4 comes along for the ride. So by making a substitution, a clever substitution, right, then I can transform this ugly equation into a much simpler equation, because now I pretend that the rest of this problem above doesn't even exist. If I give you this equation straight out of the gate and I say solve it, what do? Well, there's lots of choices. You can try to factor it and solve it. You can use the quadratic formula. You can do completing the square. You have freedom to do whatever you want. You know how to solve polynomials or quadratics when you set them equal to 0. So now that we have this in place, let's try to solve it by factoring. So we're going to open up a couple of parentheses, and we have a z squared. So this will be z, and this will be z. Multiply to give us this. And then of course for 4 I could do 2 times 2, but that's not going to add to give me 5. I'm going to try 1 times 4 because I think I may have a shot of getting this. And the only way it's going to work is with a minus and a minus. And you should always check yourself. Z times z, z squared. Inside terms gives me negative z. Outside terms gives me negative 4z. Those add together to give me the negative 5z. And then the last terms multiply to give me the positive 4. So this is the factored form of this. And so then I can say now I can solve for z. Z minus 1 is equal to 0, so that means z is equal to the number 1. Over here I have z minus 4 is equal to 0, and z is equal to 4. So far we've done exactly what we would do if I just gave you this equation and told you to solve it. You factor it, set each thing equal to 0, and get the things back. The only problem is my original equation doesn't have any z's in there at all. It has x's. So now you have to take the answers that you got and use them somehow to get the answers to the equation, to the original equation that you were given. Luckily, you made a nice substitution. You wrote it down on your paper, and you should always write it on your paper. You let z equals this. So then what I can do, since z was equal to this to begin with, is I go put it in here. Z can be substituted back into these answers because that's what z is equal to. It's equal to this. So then if I go and take this guy and stick him back in here, then I'm going to have x plus 3 is equal to 1. Because I just stick this on the left-hand side, it's equal to 1. Now I move the 3 over by subtraction, x is equal to negative 2. And I do the same substitution here. X plus 3 goes on the left-hand side, is equal to 4. And when I subtract this, 4 minus 3 means I'm going to have a 1. So the two answers I get is x is equal to negative 2 and x is equal to positive 1. So that is the concept of substitution, right? You're given an equation that looks very complicated to solve. Remember, the only other alternative to solving this equation is to literally do FOIL and blow this term out, and then to multiply and distribute this out, and then to collect all the like terms, and you would have a polynomial there that you could then solve, and you would get these answers. But this is much faster because since you recognize it's in quadratic form, if you do the substitution, you get a nice quadratic equation, which is very, very simple for you to solve. And so that's the method that we're going to use going forward. When you get down and you get your answers in terms of z, then you substitute back in to get the answers in terms of x. So now we're going to go through the rest of the lesson solving several other problems, some similar to this, some a little more complicated, but they will all have the same thing in common. You have to make a substitution, solve, and then do another substitution in to get to the final answer. And by the way, this whole idea of substitution is basically how it goes in calculus too. You have a complicated calculus equation, and you'll make a substitution to make it simpler. and then you go on with the solution from there. So let's move on and continue working some of these problems in algebra. All right, for our next problem, I'm going to call this 1b, and you'll understand why I'm calling it 1a and 1b in a second. Let's take a different equation. Let's say it's 2x minus 1, quantity squared, minus 5 times 2x minus 1, plus 4 is equal to 0. Now, this is a quadratic or an equation in quadratic form because you have some term squared, a constant, some term, and then a constant with no term there in that quantity. This equation here is quadratic in the quantity 2x minus 1, so it's the same sort of deal. So let's make a substitution to make this guy simpler to solve. The obvious one is whatever is being squared here. We're going to let some variable z, we're going to make it up, equal to 2x minus 1. Now when we do that, we get a new quadratic equation back. We just put it in here. We're going to have at that point z squared minus 5 times z plus 4 equals 0, because we just take this and everything is right here, so it's z squared and z here, and there's no z there at all. Now we know how to solve this guy, or we're going to try anyway. First thing you always try is to factor. It may not always work out. If it isn't factorable, then just use the quadratic formula. So you have a z here and a z here. 2 times 2 is 4. But wait a minute, I'm thinking, hey, this looks pretty familiar. What's going on? If I go back, once I did this substitution here, I got z squared minus 5z plus 4. Here I did a different substitution, and I got z squared minus 5z plus 4. It's exactly the same equation in z. Why is that? It's because this equation is very similar to the other one. This one is this thing squared minus 5 times this thing plus 4. This thing squared minus 5 times this thing plus 4. You see, all the coefficients of the equation, both of them are the same. It's just the thing it's in quadratic in different functions, in different terms. So the form of the equation is the same. So once you do your substitution, you actually get the same thing back. So I don't really have to go through this, but I'm just going to do it anyway. 1 times 4, and then minus minus. That's what we did last time. So if we set this equal to 0, and we set this equal to 0, and solve, we're going to get z is equal to 1 here, and we're going to get z is equal to 4 from here. Exactly the same thing as before. Now here is where it diverges, because now to get the actual answer, we have to take this value of z and put it into the left-hand side. So what we'll have is 2x minus 1 is equal to 1 here. And when we put that in over here, we'll have 2x minus 1 is equal to 4. Now I can move the 1 over, giving me 2x is equal to 2, because I add 1 to both sides. And then I can divide by 2, so I'll get 2 over 2, so x is equal to 1. And then over here, when I move this over, I'll get a 5. 2x is equal to 5, because 4 plus 1 is 5. And then when I divide by 2, I'll get 5 halves. So let me just double check myself. I have an answer of 1 and 5 halves, and these are the correct answers. So notice we get 2 answers because we had an equation that was quadratic in nature, right? We had the highest power was a square. Even if you FOIL this thing out, the highest power you're going to get is a square term. So because the highest power is a square, we expect 2 solutions. We get the 2 solutions here. If on your test you circle these 2 values of z, you're going to get the wrong answer. If you, on your test, you circle these 2 values of z here, the 1 and the 4 on this problem, same thing, you're going to get the wrong answer. Why? Because this equation is not an equation in z at all. We just use it as a tool. It's like whenever you fix a sink, you got to get a wrench out, and you got to get some putty or maybe some screwdriver. Those are just your tools. So the substitution thing is just a tool. We use it, we pull it out of the bag to make this equation simple. Then when we solve it, this is just an intermediate answer. It's not the answer to the problem. It's just intermediate to help us get to the actual answer. Again, this is many steps shorter than blowing this whole thing out and going from there to find the solution. So we're going to do one more, and I'm going to call this problem 1c, and you'll see why I'm calling it 1c in a second. What if I give you x to the 4th power minus 5 times x squared plus 4 is equal to 0? Now you might look at this and say, wait a minute, this is completely different than anything we've learned, because you have a 4th power to this equation. And it's true, we've not really learned how to solve for 4th power polynomials. But what you do know is that you should expect 4 answers, because the highest power of this guy is going to always dictate how many solutions you get, how many crossing points you get. And now again, sometimes they could be real, sometimes they could be imaginary, but you should always expect 4 answers because of the highest power of 4 here. So what you should do is start thinking about this. Okay, I'm going to show you kind of one thing here, and then you may or may not do it on your own paper. But you can rewrite this as follows. This x to the 4th power, when you think about it, you can write it as x squared quantity squared, Would you agree that this is the same thing as x to the fourth power? Yes, because when you have an exponent raised to another exponent, you multiply the exponent. So this is x to the fourth power. Okay. Then for this next thing, you say, well, I have a 5. And then I'm going to put in parentheses, just to make it clearer, 5x squared. Would you agree that this term is exactly the same as this one? Yes, of course, because you just take the parentheses away and you have what you have. And then I have plus 4 is equal to 0. So the one thing I want to point out to you, I'm just writing it this way to show you that this equation is quadratic in the quantity x squared. Why? Because when you go back here, you know this one's quadratic in 2x minus 1 because you have 2x minus 1 squared minus 5, 2x minus 1, and then nothing here. This guy is quadratic in the quantity x squared because x squared is what's squared, and then you have x squared to the first power, so you have second power, first power, 0 power. It's exactly the same form of a quadratic equation. You have to have something squared, something to the first, something to the 0, which means it disappears. These coefficients are the same. So because of the way this is laid out, you obviously want to let the quantity z, to solve this thing, equal to x squared. Why? Because when you substitute it in, you're going to have z squared minus 5 times z plus 4 is equal to 0. Make sure you understand that. So we've transformed this thing. I could have skipped this step and just told you to let z is equal to this, but I think it's really instructive to write it out so that you can see it. But you think about this, if z is going into here, x squared squared, that gives me the fourth power. This going in here, 5x squared, that's what's here, and then you have the 4 right there. So now we have to solve this guy again, the same as we always have, but notice that this equation is z squared minus 5z plus 4. It's exactly the same thing as we had here, z squared minus 5z plus 4. Again, the reason it's the same is just because these coefficients are the same. That's why I have them 1a, 1b, and 1c, because all of these equations look different, but they all have the same basic form, because they all have the same coefficients. So I don't even have to factor this thing. I've solved it so many times. I already know that, let me go, where do I want to do this? Let's go over here. I already know that z can have two values. Z can be equal to 1, and z can be equal to 4. Those are the two values. Those are the two values I got before. But I have this substitution, meaning that z is equal to x squared. So I can substitute this guy back in here. Let me switch colors over here. So what I'm going to do is put it over here and say x squared is equal to 1. Now you already know how to solve this. I take the square root of both sides. When I take the square root of both sides, I'm going to have an x on the left. I got to insert my plus or minus and the square root of 1. So x is going to be equal to, the square root of 1 is 1, so you get plus or minus 1. That's two values, plus 1 and minus 1. Here, when I make the same substitution, z being x squared, I'm going to have x squared is equal to 4. So same thing, I'm going to take the square root, and it's going to be plus or minus the square root of 4. And I know what this is. X is going to be equal to plus or minus square root of 4 is the number 2. This is two values here. So the answers that you get is plus 1 and minus 1, and plus 2 and minus 2. 4 values for a fourth order polynomial. That's exactly what you expect. Plus or minus 2, plus or minus 1 for your answers. So we have more problems left in this section, but it is important for you to understand that the main concept of what we're doing is now in your hands. You already know now the main idea. All of the other problems that we're going to do are just going to be slightly more complicated, maybe a few more steps, but ultimately you have to identify something to be substituted to transform the parent equation into a child equation that's much simpler to solve. And then you might need to do another substitution to bring it back in to the variable that you have to solve for to begin with. So let's do one more. We have, or I should say two more. X to the fourth power minus 3 times x squared minus 4 equals 0. Again, I have a fourth power, a second power, and then a nothing power, which is very similar to what I had before. A fourth power, a second power, and then a zeroth power. So I can write this, or I can think about this as, I can think about it as x squared, quantity squared, minus 3x squared minus 4. That's just the way I think about it. It's something squared, something to the first, something to the 0. So I'm going to make this substitution the same one that I just did. I'm going to let z is equal to x squared. I'm going to let z is equal to x squared. And when I do that, I'm going to transform this into this equation. It's going to be z squared minus 3 times z minus 4 is equal to 0. Now I need to try to solve this. I can do the quadratic formula, but I always try to factor first. I have a z. I have a z. I could do 2 times 2, but that's not going to be able to add or subtract to give me 3. So instead I'm going to do 1 times 4, and I'm going to try to get the signs right. So I have a negative sign here, so the only way it's going to work is like this. And you should always check yourself, by the way. The interior terms are going to give me positive z. The exterior terms, negative 4 times the positive z, will give me negative 4z. When I add these, I'll get the negative 3z. So I have z times z is z squared. The interior and exterior terms give me this, and then these multiply to give me negative 4. So that's the correct factored form. So then I have z plus 1 equals 0, or z minus 4 can also be equal to 0. So I just solve and say that z can be equal to negative 1, and z can be equal to 4. Now, a lot of students will stop here and circle, but that's wrong, because the answer is not z equals anything. The answer is you want x. That's what your problem was given to you in. So I'm going to take and substitute this in. Z is equal to x squared. So I'm going to switch colors to do that. And then what I'm going to have is x squared is negative 1. And then over here, I'm going to have, because z is equal to x squared is 4. Now let's work on this one first. Let's work on this one first. To solve this, I'm going to have to take the square root of both sides. Right? I'm going to have to take the square root of both sides. So I'm going to take the square root of the left, and the right, I'm going to have to insert my plus or minus square root of 4. The square and the square root cancel, giving me x here. So over on the right-hand side, I have plus or minus 2. Now on this side, I have to take the square root of both sides, so that's going to reveal the x here, plus or minus the square root of negative 1. So we've done complex and imaginary numbers by now, so you know the square root of negative 1 is just I. So it's plus or minus I. So the two answers I get here are plus or minus I, and the two answers I get here are plus or minus 2. So all together I actually have 4 answers, which is exactly what I expect. So if you were to graph this thing, what you would find is that you have 2 crossing points on the axis, which are at plus or minus 2. These other 2 are imaginary, and we have already explained, I've already done another lesson in what imaginary roots mean. It just means that in the complex plane, the crossing points, so to speak, are on the imaginary side of things. So the real crossings are here, the imaginary crossings are here, and if you're more curious about why sometimes you get imaginary roots, go look at my lesson on what imaginary roots mean, and I go through a lot of 45 minutes of teaching you what that means. All right, but the bottom line is you get 4 answers for a 4th order equation. So notice that the form of this was something to the 4th, 3 something to the squared, and then this guy, constant. And now I want to do one last equation, which looks very, very different, but actually turns out to be similar. So this last problem is going to be x minus 3 times the square root of x minus 4 equals 0. Now this equation has no squares in it anywhere. There's a radical in it. It looks very different than this equation, totally different than any of these equations, right? Now most people, including me honestly, if I looked at it, I would probably not know what to do. But the truth is, you can try different substitutions. You can try any substitution you want. You can make z equal to square root of x plus 2 plus 5 minus 7, anything you want. But if it doesn't make the problem simpler, you're wasting your time. So my advice is if you're given a weird equation and you want to try a substitution, just try something. If it falls out to be a nice quadratic, you've made the right choice. This one is not clear. It's not setting off alarm bells. But what I want you to do is let z equal to the square root of x. Why square root of x? Because it's the only weird thing in here. And we know if we have a square root running around in this polynomial, it's going to be very hard to solve. So by doing a substitution, we're going to try to remove the radical from our simpler equation down below by setting it equal to z. Let's just try. We may not get where we want to go, but we're going to try. Now, when you set z equal to x squared, this also means if you square both sides of this equation, that z squared is equal to x, right? Because if you let this happen and you square both sides, z squared, square root of x squared gives you this. This is exactly equivalent and comes from this substitution that you have just made. So why do I do that? Because I have an x here, but I know that x is z squared because of what I've just done. So then by putting in an x here, I'm going to actually have a first term, which is z squared. And then it's going to be minus 3 times the square root of x, but square root of x was just z. And then I'm going to have minus 4 is equal to 0. Now, this should blow your mind because the original equation is very ugly. No, I don't know how to solve that. But by doing a clever substitution, it actually turns out to be a very nicely behaved quadratic, z squared minus 3z minus 4, which actually turns out to be exactly the one we got here, z squared minus 3z minus 4. So I guess I'm doing this to show you that looks can be deceiving sometimes. Sometimes you can do these things and it's very obvious what to substitute. Sometimes, like in this one, you don't have any idea. But when you try it and you get a simpler equation, then you just go rock and roll with it because, you know, that's what you do. So here we're going to try to factor. And we know it's factorable because we just did it. So we have z, we have 1, we have 4, and we have plus and we have minus, and we've already verified this is right. So we know that z is equal to -1. That comes from setting that equal to 0. And we know that z is equal to +4 because these are the exact same answers we got before. Now where it gets a little bit tricky is going from here to the answer. Z is -1. Z is square root of x. So I can substitute that square root of x into here. Square root of x is equal to -1. Now before I solve anything further, let's go over here. Z is square root of x. I put it into here. Square root of x is equal to 4. Now, what I'm going to do is work on this one first. And you'll see why in just a second. Square root of x is equal to 4. I mean, you can think of it several ways. I mean, it's nice even number, so you already know the square root of some number has to be 4. So we know the square root of 16 is 4, so you already know that x is 16. But if you didn't know that, the way you would do it is you would square both sides of this equation, right? So you would say square root of x, quantity squared, is 4 squared, because I'm doing the same thing to both sides. So I'm going to have x is equal to 16, and you know that that's right because when you put 16 in here, that's what you get. So you get an answer of 16. I'm going to circle that answer, right? But then I go over here and I try to apply the same logic. So your first thought is going to be, well, I'm going to solve this guy. I'm going to square this and square this. The problem is, here's where you're going to run into problems. You see here, I'm getting the square root of some number equals a +4. And I know that that exists. I know that I can take square roots of numbers and get positive answers. But here, there is no value of x where I can take the square root of it and get a negative number back. Square roots never give you negative numbers back, right? The square root of 16 is 4, but the square root of -16 doesn't give you -4, it gives you 4i, which is imaginary. So there is no way to take the square root of anything and get a negative number out. So this equation, even though you want to solve it to get the other half of the solution, there's nothing else to do. This is basically impossible. I'm just going to put no solution to the side of it. There is no value of x that you can put in here to make it work. And sometimes you just have to look at what you're doing to recognize that's the case. But even if you didn't do that, let's say you just ignored that warning or whatever and you just decided to try it anyway, then what you would get here is you'd square both sides. So you would get rid of the square root and you would have an x, and you would have -1 squared because you'd square this, you'd square this. So you would say x is equal to 1. And you would probably circle this answer, and then you'd also circle this answer, and you get 2 answers and you think you're done. But here's the problem. If you go back up to the original problem and put a 1 into this equation, does it work? 1 minus 3 times the square root of 1 is just going to give you 1. So 1 minus 3 is -2, and -2 minus 4 is -6. Do that again. 1 minus the 3 is -2. -2 minus the 4 is -6. So when I put this in here, it doesn't work. So even if you don't see it here, when you get down to the end, you know, technically you're always supposed to be substituting your answers back in. Most of the time we don't substitute the answers that we get back in because for the regular quadratic equations, everything's well behaved. But when you have radicals in here and you start squaring things, then you can introduce other solutions. And so this basically is not true. And you can see it by looking at this equation and realizing there's no solution to this equation. So this equation actually only has one root. Now you might also look at it and say, well, wait a minute, I thought all these quadratic equations have 2 roots because they're quadratic, right? So I got curious about this one and I graphed it. If you look at the original equation, which is this equation, this weird one up here, this is what it basically looks like. So you have an axis like this, here's x, here's y. So f of x is equal to this minus 4. That's what you're solving. Y is equal to x minus 3 root x minus 4. This is the equation you're graphing. What it looks like is this. It starts here, and it kind of goes up like this. And this crossing point is x is equal to 16, which is exactly what we calculated. That's the crossing point, the root. But the graph doesn't even go past this axis here. Why? Because this is all positive values of x going in, but here at the negative values of x, there's nothing, the function doesn't exist for real numbers, because if you put a negative number in here, square root of a negative number gives you an imaginary answer. So when you're plotting the thing on a real axis, the function stops here. It doesn't even continue to another crossing point, because it literally stops dead in its tracks, because for any negative value of x that you put in, the function becomes imaginary. It doesn't exist as a real number. So you get two answers, technically, quote unquote, because of the substitution that you did created a quadratic equation that had two answers, these two answers. But these two answers didn't correspond to two answers in the original problem. I guess my point is, when you do substitution, right, technically you should always take the two answers you get and plug them both back in and verify they're both correct. But the real story of it is, for all of these other problems where everything's well behaved, they're always going to work fine, because the process doesn't involve any squaring or any radicals. It's really only when you have squaring and radicals going on that you can introduce additional solutions, extraneous solutions, that aren't really a solution of the parent equation. And that's why I wanted to do this problem. So you get the two values of z, you get the two solutions. Technically you would plug them back in, but here we even realize this can't have anything, so we kind of throw this away. But even if you did, you'd realize it doesn't work. If you stick the 16 in there, you'll see it works fine, because you have 16 minus 3, this square root of 16 is 4. So 16 minus 3 times 4 is 12, so 16 minus 12 is 4. 4 minus 4 is 0. So this value works. This value doesn't. And I'm trying to show you what the equation is. So here is the idea of solving equations in quadratic form. Do a substitution. If it makes the equation look like a nice, well-behaved quadratic, solve it. And then you have to do another back substitution at the end to get the final answers. And then as a check, you really should be putting everything back in to make sure. But I'm just telling you that if the equations are well behaved, they're always going to work fine. You have radicals or squaring involved, then I would always check both solutions to make sure. So make sure you understand this. Follow me on to the next lesson. We're not done yet. We're going to do more complicated problems to get you very comfortable with solving these equations in quadratic form.